Yeah.
Anil, could you do that, please?
Yeah, Anil, are you there?
I think you should let people in. They're all waiting.
Okay, yes, that's a good idea. Let's.
So Pooja, I think you'll be able to do that.
Yeah, I have done it, and Anil says it's live now. So
Okay.
go ahead, please. Yeah.
So I take it, let's see. Yes, we are absolutely live. In fact, we were live for a while. I haven't refreshed my YouTube. All right, we are live and we have an audience on Zoom. So so to Pooja, there will be people in the waiting room.
Yes, I have admitted everybody for now. Yeah. And I've disabled waiting room, so everybody will be able to join. Yeah, we don't have to worry.
Super. All right, people, welcome to yet another of the talks under the IWM Visitors Program. It gives me great pleasure to welcome Professor Loredana Lanzani, who will be our speaker today. But before I introduce our speaker, I'd just like to say a few words about IWM for those of you who are new to this. IWM, by the way, is short for Indian Women in Mathematics. So IWM is a project funded by the NBHM, that's the National Board for Higher Mathematics, and by the Committee for Women in Mathematics of the ICM. And its aim is to encourage greater participation of women in mathematics and to provide more networking opportunities for women. So today's talk is part of several programs that serve this specific goal. Since we need to move on, I will not talk about the various programs that the IWM organizes. I would urge everyone who is interested to visit the IWM website, to which there's a link on the flyer to today's talk. But just about the visitors program, this is a series that we have among IWM events, which features women mathematicians from across the world interacting with an audience that is involved in mathematics at various levels. So we are talking about people all the way from students of mathematics to active researchers in the subject. So that's very briefly what IWM is all about. And before I introduce today's speaker, just a few words about the modality of today's talk, which is that I would request at this stage for everyone, except of course the speaker, to mute their microphones. If you have a question, then I would request you to, and you would like an answer this very moment, I would like you to, I would request you to type your question in the chat box. I shall be monitoring the chat box, and if I get an opportunity to put the question to the speaker, I shall do so. But I do want everybody to know that there is a Q&A session on the subject of this talk after Professor Lanzani has given her presentation. And as always, and in particular for those who are new to this, there will also be a segment once the Q&A on the talk is over, a segment on questions that you may have about doing mathematics, about being a woman engaged in mathematics at whatever level you are in, and any concerns that you might have that the speaker can address. Okay, so uh, we are on until 6 p.m., probably slightly beyond 6 Indian time. And so with those logistical announcements, let me introduce our speaker today. Professor Lanzani is an analyst with research interests in harmonic analysis, PDEs, and complex analysis in one and several variables. She is a professor at Syracuse University, and she's currently visiting the University of Bologna in Italy on sabbatical. So she's well known for a series of works on the Sager projection on domains with rough boundary. Professor Lanzani is a fellow of the American Mathematical Society. Before she moved to Syracuse, she was a full professor at the University of Arkansas, where she had received the Robert C. and Sandra Connor Endowed Faculty Fellowship. And so with those words, we come to today's talk. You can all see the talk title already on your screens, Practical Uses of Complex Analysis. And with those words, Loredana, it's all yours.
Thank you, Gautam. First of all, I want to thank you and the other organizers, the executive committee at the IWM, for inviting me to talk at your series. This is an honor, and it's something that is very dear to me and close to my heart. Also, thank you, Gautam, for saying a few words about my research interests. That's because I'm thanking in particular because this talk will not be about my own work. It will be about other people's work. And I think for that reason, it's probably my most popular talk. So before we start, I want to explain for a moment the choice of words for the title. We're not together in person, so I cannot ask for a show of hands, but I would be curious to know whether there are many Harry Potter fans in the audience. I'm a big Harry Potter fan. I have read all the Harry Potter books at least a couple of times. Very good, Prachi. I'm glad to see I'm not alone. And just at the time that I was starting to think about preparing this talk, which has been, labor of love for many, many years, I was reading one of the little books that J.K. Rowling also wrote after she finished the whole series. I'm glad to see more hands being raised. That's delightful. And one of these little books, one was something like Wild Beasts and How to Tame Them. But then there was one that was titled Practical Uses of Magic. And then I realized that when it comes to magic and mathematics, complex analysis is probably as close to magic as one can get. And so I took the liberty of taking a cue from JK and borrowed some words in her title for this talk. So let's see, I'm going here. This is going to be the only slide that has some mathematics in it, and I ask those of you who are familiar with these concepts to bear with me. It will be just for a couple of minutes. Also to help us sort of set some notations and terminology. So if we start with the imaginary unit, I, that's defined to be one of the two solutions of this algebraic equation, very simple to state, x squared plus 1 equals 0. The fundamental theorem of algebra says that this polynomial equation has to have a solution, in fact, 2. On the other hand, if we look at the left-hand side of this equation, if we restrict ourselves to the solution x being just a real number, it's clear that we can't find a solution because the left-hand side is always going to be strictly positive, at least greater than 1, greater than or equal than 1. And so to find a solution to this equation and so be consistent with the fundamental theorem of algebra, we have to get outside of the realm of real numbers. And that's why we call one of the two solutions imaginary unit, not because it's a figment of our imagination, but simply because it's not a real number. And so complex numbers are just combinations of real numbers mediated but mediated by the imaginary unit. And here we have some examples. Of course, real numbers in particular are complex numbers. And the complex plane is a geometric, a graphic representation of all of the complex numbers. Functions of a complex variable are functions whose domain of definition is the complex plane or a subset of it and take complex values. Now, because the complex plane can be identified with the Cartesian product, the Cartesian plane, the Cartesian product of the real line with itself, and so one could think of the input and the output of a function of a complex variable as a vector with two components. And when people talk about vector valued functions, often call them maps. Very often people call functions of a complex variable maps, a map. Among all the maps that one can define on the complex planes or subset of it, there's a very special family, which is the family of conformal maps. What's special about a conformal map is the fact that on a small scale, if you look really close, if you take somebody raise their hand, I cannot see the chat box. Oh, but I think this is in response to my question about the Harry Potter fan base.
Yes.
Great. I'm delighted to see so many. Wonderful. So if we go back to conformal maps, they're special because on a small scale, they preserve the shape of objects. So if you take a magnifying lens, or if you really look close to the picture of a conformal map, you will see in particular that angles between intersecting curves in the domain of the map are preserved in their images. However, on a large scale, shapes can be greatly distorted. So your output curves may look very, very different from your input curves. But what matters is that if they intersect, if the input domain, they intersected at a certain angle, in the output domain, however different the curves will be looking, the two output curves will be intersecting at the same angle. And that's the defining feature of conformal maps. So let's give a few examples, starting from the boring ones, namely rigid motions, so translations by a fixed quantity, or rotations about a point by a fixed angle. Slightly more interesting, we have dilations. Here the constant c is a positive real number which has been fixed. If c is less than 1, the shape will be made smaller. And if c is greater than 1, the shape that you are transforming with your conformal map will be made bigger. But the more interesting ones are the inversion, the map that takes z into 1 over z. And we can see that this is interesting already by the fact that we're allowing for 0 to be an input value. And then a simple modification of the inversion, which is obtained by adding the identity and goes by the name of Joukowski map. Then finally, we will also be looking into examples that have to do of applications of complex powers. In other words, the map that takes z and maps it into z to the alpha, where alpha is any complex number, fixed complex number. It could be a positive integer, and then we would recover familiar objects. But what's of interest to us is the situation when the so-called imaginary part of the exponent, in other words, the real number that is attached to the imaginary unit, is different from 0. One can define a notion of complex power in this context, and the output is a conformal map. So let's start with a very important example. And this is an example of a conformal map which is defined on the sphere and takes complex values. So I am already contradicting myself because the first example that I'm offering has nothing to do with the plane as a domain, but it goes into 3 dimensions. However, this idea of preserving angles between curves is meaningful in any dimension. And so the notion of conformality makes sense also in this context. And so here we go back a long time ago. You see the 1st century AD. And if we go back to an idea of Ptolemy, and here we have a depiction, we'll see a bigger picture of this later. We have a beautiful depiction of it, which was made by Peter Paul Rubens in 1613. And I'm going to ask you to remember this date, which is going to be relevant to us. And so in this picture, we have a ball here, and this ball is a representation of the universe. And you see that it is a sphere in three-dimensional space, which is held by Atlas, which was a Greek god whose job it was to hold the universe on his shoulders. And you see that there is a little cherub, also known as Genius, don't ask me why, who is casting, is holding a lamp. We can't see it because the picture is cut, but it is casting a light shining through over the universe. And so, consequently, the universe is casting a shadow on the ground. And so the function that is produced this way, the function that takes a point on the universe and traces its shadow on the ground, is known as the stereographic projection. And as you can see, we have a very clear mathematical formula to represent it if we think of the ground as a representation of the complex plane. And this equation here is just there to remind us that this function is defined on the sphere. This is the equation that defines a sphere. So it turns out that this action of casting a shadow from a sphere, from a point on the sphere to its corresponding shade on the ground, is a conformal map. It is angle preserving. So before we proceed with the mathematics, I would like us to take a little break for a few minutes and talk about a historical mystery. So this beautiful image of Rubens is in fact one of 6 illustrations which he made for a book that was written by the mathematician, physicist, architect, and Jesuit priest François d'Aguillon. Here we have a portrait of d'Aguillon, and it was, as is typical of people at the time, there was no photography, so portraits were very important in order to keep a memory, to leave a memory of your legacy to the people that would come after you. So very often in their own portraits, people would ask to be represented along with the things that matter to them the most. And as we can see from the illustration that we have here, it's clear that physics and geometry, mathematics, were very important to d'Aguillon. And the book is 6 books of optics, which is regarded as the first systematic treatment of optics, by the way. So now, if we go back to Rubens' picture here and the universe on Atlas' shoulders, this picture begs a question. And the question is, you see there is a tiny little ball at the center of the universe. So what's that tiny ball? And this is when we need to remember that the book was published in 1613. Because that's the time when the controversy on heliocentrism was in full bloom in Europe. This was started by Copernicus a few decades earlier, but then it was reignited by Johannes Kepler just 4 years prior to the publication of the d'Aguillon book. And so based on this historical context, it's clear that there can only be one of 2 answers to our questions. Namely, the center of the universe is the Earth, or that would be the geocentric theory, or the center of the universe is the Sun, and that would be the heliocentric theory from the Greek name for the Sun. The picture in the book, it doesn't say, there is no caption, and there is no particular reference to the significance of this tiny dot in the book. So let's see if we can put on our PI, our Sherlock Holmes hat, and see whether we can come up with a few arguments in favor or against one theory or the other. So what can we say in favor of the answer that that's a geocentric universe? Well, first of all, at that time, the Catholic Church was a major political and economical power in the whole Western world, and it supported geocentrism. At the same time, Daguillon was a priest, so he was a member of the Catholic Church. And we must not forget that those were times when it was really dangerous to disagree with the Catholic Church. I'll just remind us that only a handful of years earlier, in 1600s to be precise, the scientist and philosopher Giordano Bruno was burnt at the stake in my own hometown. There is a square named after him, and the square is where he was burnt at the stake. The reason why is that he supported heliocentrism, and even worse, he postulated the existence of other solar systems, and those were considered very dangerous heresies. What arguments can we make in favor of supporting the heliocentric theory for that picture? Well, first of all, it was a theory that was supported by most scholars, including Galileo Galilei, who would later withstand trial for this belief. And exactly 20 years after the publication of the Daguillon book, he was sentenced to lifetime house arrest. The reason why I'm bringing Galileo Galilei in is because it turned out that he was a personal friend of Rubens. In fact, they met in, you see, a few years prior the publication of the book in the beautiful city of Mantua, which is off the tourist routes, but I strongly invite you to visit once this pandemic will be over. It's a jewel, it's a gem. And gem among the gems in Mantua is the court of Vincenzo Gonzaga, the Palazzo Ducale. He was the lord of the city, and Rubens was artist in residence during these years. It's a beautiful series of oils and frescoes that he made for the Palazzo Ducale. And Galileo was the court's chief astrologist. Even though universities existed already, the University of Bologna in particular existed, there were so few students that teaching at the university was not really a mainstream kind of profession for a scientist. And so many scientists would get by just be writing horoscopes for powerful people. And Galileo did this for Vincenzo Gonzaga. And so Galileo and Rubens met there in Mantua during this time, and we have their correspondence which lasted throughout their lives. As another argument in favor of the heliocentric theory for that picture is the fact that, yes, Daguillon was a priest, but he was not just any priest, he was a Jesuit. And Jesuits supported all scientific pursuits. And they even awarded Galileo an honorary title, which was, of course, withdrawn when he was sentenced, to house arrests for the rest of his life. Of course, Daguillon and Rubens had very good reasons to avoid taking sides in naming the center of the universe in the picture for the book, because saying that the center is the universe would alienate the Catholic Church, but saying that the center is the earth would alienate most scholars, which were the book's main customer base, either because they would purchase the book themselves or because they would curate the library of some very rich lord that would support them. But so can you even imagine the heated discussions at the time that the book was published? And, I remind you that these were the times when people would actually duel to the death to claim authorship of the solution formula for the cubic equation. I strongly encourage you to read up on the Cardano and Tartaglia dispute. And so, for the longest time, it's taken me, a good 10 years to put this lecture together in my spare time. For the longest time, I was unable to find the answer to our question, what is at the center of Rubens' universe? And I had almost given up. And then just a couple of weeks ago, in January of 2022, I visited the Museum of Astronomy here in Bologna. Specifically, it's called Museo della Specola di Bologna. And that's where I found a whole room full of objects that looked like the universe depicted by Rubens in the picture. And so I learned that the correct name for what I was calling Rubens' universe is armillary sphere. Rubens' universe is a depiction of an armillary sphere. Armillary comes from the Latin word for the armband ornament, armilla, that people like to put around their arms or around their wrists. And here we have a picture of a beautiful, huge armillary sphere at the Galileo Museum in Florence, just to stay on our theme. And so, you know, the docent that was guiding me at the museum put me in touch with the museum's science expert, and that's Professor Paola Focardi, whom I asked the question, what's at the center of Rubens' universe? She looked at it and in no time came back to me a couple of days later and she said, that's of course a geocentric armillary sphere. And it's a really simple one to boot because it's just depicting the Earth, the ecliptic, and a few celestial parallels. And so when I asked Professor Focardi, okay, this is great, but how do you know that the center of the Earth is of the armillary sphere is the Earth and not the Sun? She replied, that's a good question. And the reason why I know is because of the angle between the ecliptic, which is this big ribbon here, and the celestial parallels, which are this, guys. And so the size of this angle and other things, which I am unable to translate in English, it's technical astronomy language in Italian, gave her the absolute certainty that this has to be a geocentric armillary sphere. And, you know, after she answered my question, she actually had one for us. And her question was, okay, but what's the stereographic projection doing in a book about optics? And so it was my turn to say, good question. But I've decided that we're going to leave this question for another story and move on. So let's go back to the mathematics, or rather to the applications of conformal mapping. And the first one that springs to mind, especially coming back from the historical context that our mystery took to, is cartography. The goal for the moment is to design a flat map of the world that sailors can use to navigate the oceans. So, you know, we're just a few decades after the official discovery of the Americas. And so there was this rush to go there and to get there, you know, to navigate through the oceans, to get to Americas and exploit its goods and its people, as it turned out. But how do you do it if you don't have a map? And so that was a major goal at the time. So the first method is to squash the world on a sheet of paper. Let's do it with an orange, and you get something like this. If you do that for the world, then you will get this kind of map. And so, of course, there are good news, and the good news is that areas are preserved. By squashing this orange peel, we don't change the surface area of the peel. The bad news, though, remembering that this is supposed to be applied science, so a sailor is supposed to use it to travel the world. And so the bad news is, how do you sail through a cut? After you pass through the very dangerous Tierra del Fuego here, and your goal is to go back to Spain and bring lots of riches to your sponsor, how do you do that if you have to go through this piece of the map? How do you read the map to go from here to here? So not a very useful map from the point of view of navigating the oceans. Another method is instead to use the stereographic projection. So here is another representation, and for those of you who are wondering who is this little fellow here, I believe that's a picture of Henri Poincaré. Anyway, what we have here is a map of the world, and as you can see, an Americentric map of the world by Rand McNally, which has been obtained by a projection, which is, however, not really the stereographic projection from a point, but it's rather a Mercator projection from the explorer Mercator. And the way that is obtained, if you think of the Earth as a ball, you take a huge sheet of paper and you wrap the ball around the equator. So now you have produced a cylinder. And the cylinder touches the ball at the equator, the Earth at the equator. And then you do your projection not from a pole, but rather from the center of the Earth. And then when you're done, you take out your sheet, and what you have is the image that we see. So of course there's some good news. There are no cuts on this map. But there are also bad news, because the area distortion, remember when I was saying earlier on that on large scale, conformal maps can distort shapes. So the area distortion on large scale is huge. In particular, if we look at Greenland and Africa. By the way, here is my favorite gripe. How corny is it for Rand and McNally to paint Greenland green? But never mind, moving on. If we look at this picture, at this map, Greenland seems to be pretty much the same size as Africa, if not possibly bigger by just eyeballing it. But then, if we actually look at numbers, I don't know if we have any volunteers with a cell phone, a smartphone close at hand in our audience who are willing to take a look at what's the surface area of Greenland and what's the surface area of Africa. If we don't, I can provide it, but I wonder if we have any volunteers that can find these two numbers for us.
Geeta, you need to unmute yourself.
I'll do it. I'm just finding the area.
Great, thank you, Geeta.
So the surface area of Greenland is 2.166 million square kilometer. And the other one is Africa, right?
Yes.
30.37. Africa is much bigger.
Thank you, Geeta. In fact, let's be generous. Let's say that Greenland is 2.2 million and Africa is 30 million square kilometers.
Yes.
So Greenland is, or let's say Africa is bigger than Greenland by a factor of about 15. But we would never be able to tell from this map. So that's definitely bad news, right? Areas on large scale are badly distorted. But the good news is, remember the application we're interested in. We're interested in we're in the 1500s and we're interested in navigating the oceans. And so the good news is that one really, within that particular context, historical context that we have described, one really doesn't care. Small scale works fine. I'm a sailor on this little wooden boat that's gonna do 50 kilometers in a day if we're lucky. And so all that I care about is small scale. And small scale is fine with the stereographic projection. So for instance, this is what people call here a polar stereographic projection. It is used for navigating the polar regions. And I want to bring to your attention that on this projection, Greenland has definitely been put correctly into perspective. It is much smaller than the previous map. And so the scale is correct, or very nearly correct, near the North Pole, which is the center of the projection. And it increases away from the North Pole, as does distortion of area and shape. But the point is that you wouldn't use this map to navigate around, say, the island of Sicily, to navigate around the island of Sicily, you would do a new stereographic projection that is centered at some point on or nearby Sicily. And just a little observation to confirm what we were saying earlier on about the fact that the stereographic projection is conformal. You see that what we have drawn, the circles and rays that are drawn on this picture are the shades that are produced by the parallel and the meridians on the spherical Earth. And you can see that they all are at 90 degrees angles, which is just what happens on a globe. And so to end this chapter, when one works with stereographic projection for drawing maps, localization is key. This is an interesting picture of the inverse of the stereographic projection. Conformal maps are invertible, and so in particular the stereographic projection is an invertible map. And so what we're seeing here is a picture that represents a neighborhood on our planet, a flat, so to speak, neighborhood, wrapped up around a sphere using the stereographic projection. Of course, there is huge distortion here, as we can see from a distance. Look at this curve. However, a person that lives in this neighborhood, let me see if I can make this a little bigger. You see that there is a tiny human here. So there is a tiny human on this sidewalk, and the human on that sidewalk, from the position where they are, will not be able to see the distortion. Okay. So let's look at now another application of conformal maps. And this is the application to Droste pictures. Okay, first of all, a little comment on this picture. I don't know how many amongst you are familiar with the Dutch cocoa maker by the name of Droste. I don't know if I'm pronouncing the name correctly, and I apologize if I'm not. So anyway, Droste is a very famous chocolate product maker, dating back to, I think, about a century, if not more. And this in particular is a very famous box. It's the box of cocoa. You can see the whole box here. Cocoa powder for making hot chocolate. The lady that's holding the tray is not, as I thought in the beginning, a nun. She's actually a nurse. And the reason for the big hat that she is wearing is because of Florence Nightingale's contribution to the science of nursing, to nursing as a science. She was the first to realize, she was a nurse and a statistician and a social science promoter. She lived in Victorian England. She was born in 1820, died in 1910. And among other things, she helped design hospitals. And she realized that fresh air circulation is key to the well-being of patients. And so she thought of all possible ways of improving air circulation in hospital wards, one of them being having nurses wear big hats. And here you have it. So anyway, if we take a look at this picture, this picture gives the name to the so-called Droste effect, which is a repeating visual effect that occurs when an image contains a copy of that same image, which in turn contains a copy of that same image, etc., etc. And we can see that we have an image here, and then we have a copy of that image in there, and presumably there's another copy in there, and so forth. So, Droste pictures have a center. How do we find the center of a Droste picture? We pick any point in the biggest picture. Here I like to pick the tip of the nose of the nurse in this first picture. And then I go ahead and I locate the same tip of the nose in the next iteration, and on and on and on. So you obtain a sequence of points, in this case a sequence of nose tips, but it could have been a sequence of elbow tips or whatever you like from the picture. And it turns out that this sequence converges to a limit point. And this limit point is independent of the particular object we choose to generate our sequence. And this is the center of the Droste picture. A Droste picture also has a scaling factor, and it is the ratio between the size of any object that you pick, of your liking in one image, say for instance the height of the cup on the tray, and the size of that same object in the next iteration of the image. And so eyeballing the Droste Cocoa Box image gives us a scaling factor of about 6.5. And now we get to the conformal mapping side of Droste pictures. It turns out that Droste pictures with center, say, at the origin, we decide that the converging point of those nose tips is the origin, are obtained by applying the exponent, this conformal map, this complex power, choosing a complex exponent that has an imaginary part here, the number that comes attached to the imaginary unit, that is related to the scaling factor. And so the idea is that you start with an incomplete rendition of the original picture, in this case, the picture of the nurse that holds a tray with a cup and an empty spot next to it, and you apply this conformal map. And so for the Droste Cocoa Box, we would have this map. And then you keep doing that over and over. And the reason why the empty spot that you started with is filled by iterating the image infinitely many times, and so we're considering this sequence of iterated maps, is due to the fact that if the imaginary part of the exponent is different from 0, then the complex power z to the alpha will take a line segment and spin it into an infinite spiral that is centered at z0. Now, in any practical visualization of a Droste image, there are technical constraints, for instance, limitations of the printer resolutions or limitations of our human eye resolution that prevent us from detecting this iteration forever and ever. In particular, the larger the scaling factor, the fewer the number of iterations of the image within image that we are actually able to see. So keeping this in mind, let's turn to art, and in particular, let's turn to the work of Maurits Cornelius Escher, well known to anyone who has an interest in mathematics. He was a graphic artist, and to stay in theme with the Droste Dutch chocolate, he was also from the Netherlands. And so among his many artworks, he made one that is particularly striking, not just because the name in Dutch is really hard to read, I'm not going to try, I'll say it in English, print gallery, but because of the image itself. So let's try to describe it. We have a young man who is looking at an exhibition gallery in a building, and he's looking at one particular print. It's a print of a seaport. And as his eyes follow the quayside buildings shown in the print, you see the print is here, he discovers among all this building the very same gallery in which he is standing. Note that there is a very mysterious empty spot at the center of the picture. And so fast forward to 2005, here is what sounds like the beginning of a joke, because you have an artist, a mathematician, and a computer scientist sitting together at a pub over I don't know, a pint of beer, and after one or two beer too many, they postulated that Escher's print gallery is in fact a Droste picture with this huge scaling factor of 256. And so, an idealized, that is to say, a completely filled version of this print should be obtainable by applying this conformal map. Now, the large size of the scaling factor, 256, as we were saying earlier on, explains the empty spot in the original picture. It would have been a too detailed, already second iteration to be filled by hand into the tiny spot. But what these people did was to, you can't really prove a theorem that says Escher's print gallery is a Droste picture with this scaling factor. But what they did, there was a computer scientist and an artist in the team, so they were actually able to write code and carry over a few more iterations. Let me see if I can do this clicking the next button. And so you see that this is what they were able to get. And you see that even at the end of the 8th iteration that they were able to produce this way, you still have an empty spot, as you should, because this is, an improvement over the original number of iterations, but finite nonetheless. Let's do one more. Let's talk about one more application of conformal mapping, and this is to do with aircraft wing design. So what's the problem? Okay, the oceans have been conquered thanks to the stereographic projections and the maps that it produced. So what's the next frontier? The next frontier is the skies. And so the goal is to design an airplane, an aircraft wing that produces a force which is known as lift that is strong enough to keep an airplane up in the air. So it turns out that one factor in this process is the shape of the airflow that surrounds the wing. And the actual physical law at play is known as Bernoulli principle. In words, Bernoulli principle says that the airflow is determined by the shape of the airfoil, the wing cross-section. So how does one come up with a cross-section shape that will successfully obey the Bernoulli principle? The idea is to apply the Joukowsky map, here it is, to a circle. And this will give us an airfoil and allows us to study the effect of the airflow, these yellow lines that surround it. So this is a picture that I have lifted from the NASA website. It is not a very precise picture. I have no idea what this blue perpendicular lines stand for. You see that because we have 1 over z, this cannot be the real and imaginary axis, and this cannot be the origin because it would be blown up to infinity by this map. So I don't know what this stands for. But it gives us an idea that the position, we have this ideal airfoil, which is just spherical, like a cross-section of a cylinder, and we see how the airflow moves around it. And then if we apply the conformal map, this conformal map, we get a different shape, and we can follow the corresponding airflow until we find the shape where the airflow matches whatever is required by Bernoulli principle. The point here is that if we change the center of the circle, if we move the circle around and we keep applying this map, the corresponding image points will change the airfoil. They will wiggle around. They will look like a moving fish. And among all the shapes of the moving fish, there will be one that works. And so here there is a whole collection of airfoils that work, and you can see the years when they were produced. The one that matters to us is this one, produced by Joukowsky in 1912 in Göttingen, using the conformal map that is now being named after him. And now for the last topic, what I used to call whimsical conformal mapping. And this has to do with the work of Darcy Wentworth Thompson, here portrayed as a young man sporting a whimsical curl, we could say. He was a biologist, mathematician, classic scholar, and an explorer. He was a Renaissance man. He was a polymath. We can think of him as some sort of a real-life Indiana Jones, for those amongst us who are fans of Indiana Jones. And here I've picked this particular movie, Indiana Jones movie, not because it is particularly good. The hardcore fans tell me that this is probably the worst Indiana Jones movies ever made. But I couldn't resist it because look, Indiana Jones here is wearing the same hat as Darcy Thompson, and both of them are sitting on some kind of mysterious archaeological dig. And so Thompson's main opus is the 1917 book On Growth and Form. I forget, I think the publisher is Oxford or Cambridge University Press. I forget who is the publisher. It's off the top of my head. I can't remember, but it's on that scale. And it is their most popular book. The first edition goes back to 1917, and I think the latest edition appeared just a handful of years ago. So among the many, many things that On Growth and Form explores is the extent to which different species of related animals can be described using what it refers to as conformal transformations. And so you see, these are pictures from the book, and they should be looked at in couples, so like this pair. And so here you have two existing fish species. And what he did, imagine that you're drawing the contour of your species on a rubber sheet and that you mark a grid. As you can see, you have a grid of rectangles on this rubber sheet. And then what you do is stretch with your hands. You stretch the rubber sheet in a certain way along certain directions. And if you do that, the corresponding picture that you get gets also stretched. And it turns out to be the picture of another existing fish species. And as you can see, he did this with different kinds of fish. All right, so these pairs of fishes are said homologous. As we said, you get one from the other by applying this kind of stretching over a rubber sheet. And these are maps that have to preserve a given number of what people call landmark points. Typical landmark points would be, for instance, the eye. The eye has to be mapped to the eye, and then the tip of this fin has to be mapped to the tip of this fin, and so forth. Now, it's clear that none of these images can be obtained via a conformal mapping. And that's because, as we can see from the pictures, the angles in the grid are not preserved. And we know that conformal maps have to preserve angles between intersecting curves. The reason why they cannot be conformal, besides this visual inspection, is because in order to get this picture, you need a lot of landmark points, but a conformal map can guarantee only 3. And so I thought that was the end of the story, but once again I was proved wrong. In 2013, I was at Brown University, and L. Mahadevan, who is a professor of physics, biology, and mathematics at Harvard, a MacArthur Fellow, you could say a present-day Indiana Jones, was presenting his work with his postdoc at the time, G.W. Jones. And I wasn't aware of this branch of math biology that is known as morphometric analysis, in particular, planar morphometric analysis. Morphometric analysis is the study of how living organisms evolve over time. And planar morphometric analysis focuses on organisms that can be accurately described using only 2 dimensions. So fish and leaves. And their work was, in particular, the talk was about leaves. And what Mahadevan and Jones postulated is that certain homologous species of fish or leaves can be morphed into one another, not by means of a conformal map, but by means of another related mathematical concept that is the concept of quasi-conformal map. Quasi-conformal maps allow for controlled angle deformation. In other words, angles between curves are allowed to change somewhat. And they also allow for lots and lots of homologous landmark points, eye to eye, tip of the fin to tip of the fin, etc. So those are the great feature of conformal maps, quasi-conformal maps. The problem is that constructing a quasi-conformal map by prescribing homologous points and giving a range for the angle deformation will give you lots and lots of choices of maps, what people call competitor maps. There are too many. And so then the problem becomes, how are we going to figure out which one is the particular quasi-conformal map that Mother Nature implemented in order to generate, fish species A into fish species B? And Raghavan's and Joan's idea was to apply Thompson's criteria for map selection, which seemed very reasonable to me, at least the first one. Actually, both of them. The first idea, the first criteria is that the grid deformation should be as simple as possible. And Raghavan and Joan's job was to somehow produce a mathematical model for what it means for a grid, deformed grid, to be as simple as possible. And the mathematical notion they used was the notion of local shear. Secondly, the second criteria is that the grid deformation should also give insight into the physical process of the change from one species to the other, the physical process of shape change, by providing a mathematical model for the forces that drive the change. And the mathematical model, according to Thompson, to Raghavan and Jones, is the process of minimal variation. It should have minimal variation. And then the task is to implement a variational principle that leads to a numerically constructible solution. So this is a solution for which there's not going to be a beautiful formula like z plus 1 over z. You can only represent it approximately graphically. And so they decided to test their numerical solutions on the very pictures presented in Darcy Thompson's book. And this is how they did it. So here we have the original picture from the book, and we have identified 1, 2, 3, 4, 5, 6, 7 landmark points. And so what they did to test their code, their numerical solution, was to take the original species A fish and fill it up to the extent possible with little discs. I don't know what's the meaning, the significance of the different colors here, the shades, you see, I don't know. So they filled it up with little discs. And then to this collection of little discs, they applied their numerically determined quasi-conformal map. And this gave rise to this little ellipses that you can see here. And then what they did next, they took the output picture from Darcy Thompson's book and overlapped it with the little ellipses and realized that there was a pretty good match in the sense that the ellipses fit the picture, don't get out of it. They can't explain the reason why there seems to be some particular angle to the axis of this ellipses. There must be a reason for that. The fact that circles are mapped to ellipses is typical of quasi-conformal mapping because you change the shape a little but not much. But the reason why this axis seemed to be a little tilted remains unexplained, at least at the time that they published their paper. And so this ends the mathematical survey of this talk. I have some references for you, for those of you who might be interested. This is an output of the pandemic. Here, the National Library of France, I just discovered a few days ago, has a marvelous series of virtual exhibits. And one of them is perfect for the first part of this talk because it's about spheres and it has a whole section on armillary spheres. This is another virtual visual exhibit, but this one on the armillary sphere is really beautiful because there are animations. Here there is a virtual exhibit on the history of cartography with beautiful pictures. And then we have, the article that I drew mostly from by Stephen Kranz on the American Scientist. This is the report on the experiment about, the Drosty effect in one of Asher's pictures. This is the article by Joan and Raghavan. And for those of you who may have time, on YouTube, there is a very beautiful animation of conformal mapping composed with the stereographic projection for a family of maps that we haven't had a chance to talk about, the Möbius transformations, but probably many of you have heard of. And it's a joy to look at. It's only one of the very few mathematical videos that I know of on YouTube that has more than 1 million views. And so if I have just another minute, this would, but as it happens, and here I want to recall with Professor Barali, Gautam, when we made arrangements to give this talk on this particular day, this was back in September, and we had a lot of back and forth, this date will work for me, this date will not work for you, and on and on. And we finally settled on February 9th. And I thought, okay, that's just a date that works. But there's more to it. I think there is a little bit of karma. The reason why I'm saying there is a little bit of karma, I think this talk today was meant to happen. Because as I was reviewing my slides of Monday, I just became aware of the fact that this Friday, the day after tomorrow, February 11th, is the International Day of Women and Girls in Science. And this is a day that's been first, instituted in 2015 by the United Nations. More to the point, to celebrate February 11 this year, the OWSD, Organization for Women in Science in the Developing World, in partnership with the International Research Council, will host an online film festival with 10 short films that are going to feature women scientists. And I invite you to peruse the festival. I will do the same. I'll try to do the same on Friday. But I'm being told that the link will not be, the URL for the streaming will not be active. It will not be activated until the very day of February 11th. So all we can do for now is just bookmark it and save it for 2 days from today. And this is the poster. The registration, my understanding is that the registration and the streaming time applies only to a panel discussion. But I think that all the films starting February 11 can be viewed at any time during that day. And with that, I thank you for your patience. Thank you.
Thank you very much. So before we move to questions, let us thank the speaker online.
Thank you.
And so Loredana, you might want to know that I received several direct messages through the chat box complimenting you on this talk, and I had mentioned in response that the speaker had insisted that she has chosen not to speak about her own research, but to speak on a classical topic, and several people have DM'd me appreciating the decision. So let me share that appreciation with you. And I will now throw this open to the audience. Questions, please. So do remember that to ask, you'll have to remember to unmute yourself. Okay, so let me begin with a question which I kind of didn't follow a point that you made about the constraint on choosing landmark points if one is looking for a angle preserving transformation when one is choosing a deforming map that is rigorously conformal. I didn't follow the point. Why 3 points?
So no, in fact, you need more than 3 points. You need to prescribe in order to produce the kind of deformation that we have seen in those pictures. You need to prescribe many points. But with a conformal map, you can only prescribe up to 3. So it would be inadequate. Besides the fact that we can visually see that the angles are not preserved, you wouldn't be able to find the conformal map that maps Z1 to W1, Z2 to W2, and Z100 to W100. Now, why do you need more than three landmark points? That I wouldn't know. That's part of the technical aspect of it. But what is stated in Raghavan and Joan's paper is that 3 points are not enough. And therefore, this provides some kind of theoretical substance to the claim that the pictures we see in the original book cannot be conformal besides the visual from the grids.
Right.
Can I ask a question?
Go ahead.
Yeah. Hi, that was such a lovely talk. I couldn't attend the beginning because I was stuck in another meeting, but I think I caught a lot of it. I just wanted to, on the same kind of line that Gautam is asking, so when you come to quasi-conformal maps and that, they chose some landmark points on the fishes and created the numerical quasi-conformal thing. And so what happens if you change the number of landmark points that you choose on that?
That's another good
question.
Something
else, or does it still converge to the same kind of thing?
I don't know. One guess that I would be willing to offer is that if you choose, changing the number of landmark points might change the number of competitor maps that you produce, among which you then have to choose.
Right.
That could be, one of the,
wouldn't it go down rather than up if you chose more points?
That's a very good question, because of course you want to pick the minimum, right? You don't want to do 1 million landmark points if you can go with 7.
When you do the numerical, the two aspects that are that they have the minimal variation, and there was one more thing there, right?
So the grid should be as simple as possible. So it should be a shear.
Yeah.
A shear map. Yes.
That would still apply, right? So that would
I think
out the competitor maps. So within the same thing, what happens when
I don't know.
That would be really interesting to know.
Yes. And I want to add to this, which I found out a few years ago. If you're interested into the mathematical modeling of planar morphometric analysis, which sounds like you are.
No. It is the first time I've heard about it, and it sounds interesting.
And so my understanding is that there is, or at least a few years ago, there was a large group at Duke University working on this in Ingrid Dobeshi's team.
Okay.
And so I remember giving this talk for their Women in Mathematics club. But then it turns out that because I mentioned, Raghavan's work, I had a whole bunch of professors and graduate students in the team coming to the talk. And they mentioned that they have, several papers. So this 2013 paper that I'm quoting, there has been a lot of work that has followed up on it, and now there is a whole slate of papers. And I encourage you, if you're interested in pursuing this, which I think it's fascinating to look up into the Dobeshi's research teams and see which one is working on planar morphometric analysis. Chances are that maybe some of
They
the
would have
answers to
already-
your questions
Yeah.
might be there.
Thank you.
You're very welcome. And I'm sorry, Gita, that I can't be of further help in
No, I
clarifying.
mean, it was just something that occurred after Gautam asked his question. So I suddenly thought about this and then I wondered what happened. So,
Of course, there is the numerical side to it. So in terms of the
yeah, I mean, I was just wondering
computability,
whether it sort of makes you converge faster.
yes,
to the thing
exactly,
rather than change.
So you get your picture in 1 hour instead of 2 days, or something like that. Yes.
Maybe something like that. And
Exactly.
yeah, or you could do a subset of landmark points and then see what happens as well. So that would also be interesting. Yeah.
Are you an applied mathematician?
No. I'm a group theorist. But
I'm impressed.
no, but this, I mean, I think it's maths. It doesn't matter whether it is.
That's true. That's the beauty of it.
Yeah,
the universality of it, right?
Yeah. I'm just so excited today because I took my first physical class after 2 years. And
that's marvelous.
And I could see my students reacting to my teaching, and I obviously didn't do as much as I thought I would do in the class.
Doesn't matter. It doesn't matter.
And I felt so thrilled.
Absolutely.
It's been a good maths day.
Absolutely.
Yeah. Sorry, there are lots of questions in the chat box, Gautam.
There is something about a reference.
These are comments. So here is a comment from Cheyenne Ghosh. Which book is more preferable for reading several complex variables from a topological viewpoint?
From a topological view, I think, Gautam, this one is for you.
I see. Well, okay, Shan, let me try to answer that question. And that is, I don't know what you meant by topological viewpoint. Do you mean a book that focuses on several complex variables from an explicitly geometric perspective? Or do you mean a book where the focus of the subject is less on inequalities, which is a very important trend in several complex variables? Okay,
I read here homotopy theory.
Mostly on homotopy theory. And I would actually say, Shan, you are out of luck. You are asking the wrong person. Primarily because so if one is talking about the intersection of stable homotopy theory and several complex variables, then the intersection of these two fields really is in the realm of algebraic geometry. But to not completely sort of evade your question, since I don't even know in what sense you are using the word homotopy theory. In fact, are you talking about the field of homotopy theory in the broad, or you are talking about an aspect of several complex variables where there is a focus on the homotopy forms of theorems? In that case, I do have just the book to recommend to you. I will speak it out and I'll also type it up in the chat box. And this is the classic by Raghavan Narasimhan, which is simply called Several Complex Variables. It is extremely topologically driven. And in particular, if I understand correctly what you mean by homotopy theory, there is a fantastic section on what's called a generalized monodromy theorem. which is one of the applications of homotopies between curves with fixed endpoints. So I don't know if that's the sort of stuff you're looking for. Also, the approach is not on estimates, but on topological concepts. So maybe this is the sort of book you're looking for. I repeat, Raghavan, Narasimhan, Several Complex Variables, University of Chicago Press, and I'll also type this up in the chat box. Okay, so here is another question. So there are lots of comments, and I'm trying to, yeah, so Riddhi DMs me. Erin wanted to ask an informal question. So Erin, go ahead. Are you still in the talk? Please go for it. Okay, so since, okay, I think what Erin, I think I can infer her question. I wish you were around to ask it, because I see a comment by her. It would be very interesting if we would have done some anime discussion.
So applications of conformal mapping to anime, that's terrific. I wished, I take suggestions here. If the person who asked the question has one particular movie in mind where, you know, the anime illustrations somehow are relatable to conformal mapping, I would love to follow up on that. So I will leave it to you, Gautam, if you have any follow-up on that question. Any suggestion for particular movies, I will definitely look into it. Thank you.
So I have a direct message, and I recognize the name, but I don't recognize, this is probably a title. So, oops, where did it just go? Hang on a minute.
I'm here writing it up as you speak.
There's one more question in the chat about the particular conformal map which was used in aircraft.
Right. So in fact, that was the question I was focused on till I saw Riddhi's DM. So the term that I used, the term that is vaguely familiar to me, because it is a technique of rendering called Shinra tensei.
So can you write it on the chat so that
let me do that, and let me actually to send to everyone in the meeting. So what little I know, Shinra tensei is a technique of rendering. It is and that's about all that I know. That's as far as my knowledge goes.
All right, I will pursue this. Thank you.
So I will move to the next question, which is from Annapurna. While describing the aircraft design as an application of conformal maps, why specifically the map Z going to Z plus 1 over C?
That's a very, very good question, Annapurna. Thank you for asking it. I would say, my guess, I don't know why Joukowsky devised this particular, I don't know how he got to devise that particular map. It's named after him, so I'm guessing that he was the first one to come up with it. But from a practical point of view, if indeed airfoil was the true motivation for this pursuit, so then he had a general idea of what the cross-section of an air wing should look like, a little bit like a, what's the word? Like a drop-shaped, section. And so then the question that he posed himself was, what kind of algebraic, meaning, map for which I can give a formula, no numericals, just, specifically formula-driven map, can I come up with that's going to take a disk to a shape that looks like a little wiggling fish, or, like a drop, and as close as possible to what we think is going to be a functioning air wing. And I think that based on that, he started to experiment with conformal maps, and he realized that z plus 1 over z is the one that does it, and that the change of the fish-shaped figure will happen if you move the center of your disk. So I would think trial and error.
So I had a comment on the question asked by Geeta, because in fact it is after I saw your abstract that I realized, I mean, morphometric analysis was a phrase I was seeing for the first time when I saw your abstract. I think I have an idea of how Dobeshi's team is involved in this, because in fact, you have images where you need to focus on varying scales based on different parts of the image. One of the things is one can glue quasi-conformal transformations that are localized. And I think since this is a, how do I put it? This is sort of an inverse problem where you're trying to guess the quasi-conformal map based on a certain variational principle. Apart from the two principles that you stated, might as well sort of factor in the information about how much, how much of the scale is going to dictate the details of the transformation. Since we have at our disposal whether to use few or more landmark points, that's sort of the next evolution. So which is very much up the alley of the group that you named. So just to follow up on your response to Geeta, that's where this particular group comes into the picture.
Mm-hmm. Mm-hmm.
Okay, more questions?
Gautam, I have a point to share.
Go ahead. Please go ahead.
Oh, okay. Video is not working. That's okay. You mentioned about you compared the pictures of two types of fishes, two species of fishes, and you mentioned about a branch called some metric analysis.
Planar morphometric analysis. Yes.
Yeah. Essentially, that belongs to what people call evolutionary biology.
Yes.
And recently, there is a group of math biologists from University of Harvard under Martin Nowak, who publishes usually in the journal Nature, that the origin of species and the principle of natural selection could be explained by graph theoretic techniques. Quite surprising.
Wow.
And that has resulted in a new branch called evolutionary graph theory.
Oh, this is very exciting. So a lot of things.
Pardon?
A lot of things have happened since 2013. Yeah. That's in fantastic.
Fact, Martin Nowak has plenty of publications on this aspect of evolutionary graph theory. Martin Nowak from Harvard.
So you said evolutionary graph theory.
Yeah, evolutionary graph theory. I work in graph theory.
Oh, I see.
Yeah, so this is very surprising and exciting information to share.
Oh, that's fantastic. Thank you, Ambat. So maybe I have a question for you. Isn't there a branch of, I forget whether it's biology, where people design evolutionary trees?
Yeah.
so that you want to sort of trying to guess how a certain species is going to evolve over time.
Yeah,
And
you mean the phylogenetic tree.
Yes, exactly.
You mean the phylogenetic tree.
Yes, exactly. Phylogenetic,
Yeah.
designing phylogenetic trees, hoping to get a glimpse into the way that an existing phylogenetic tree might evolve. Is that so? I remember a long time ago hearing something about that.
I have to think about it. Anyway, we'll correspond through email and
All right.
continue the discussion.
Thank you, Ambat. This is exciting.
Thank you. Thank you. Nice meeting.
So here is another question in the chat box. And in fact, this is the question that I too had. And Loredana, I think this was implicit in your comment on the drawing from NASA. And the question, this is from Adiba Naz. What is the image of the open unit disk under this particular conformal map, Z going to Z plus 1 over Z? So that, of course, I can answer to Adiba, because if you say open unit disk, in the absence of any information, this also means the unit disk centered at the origin.
That's how I would interpret it.
Yes. And so, Adiba, you sort of see that the 1 over Z has a pole at the origin, so you'd get a huge unbounded image. But to build upon that question, maybe going back to Zhukovsky's own work. So this is, the airfoil happens to be the image of some open disk. It cannot be an open disk that has the zero anywhere in its interior. So what is the model disk here?
I don't know. That's an excellent question. In fact, the question would be, if we look at that picture from, with the list of different airfoils and the one that's being attributed to Zhukovsky, right? There was a picture with a bunch of airfoils and with the person responsible for designing it. And there was one in 1912 that was due to Zhukovsky. So what's the model for that airfoil? What disk did he use? What center and what radius did he use? I don't know. That's a very exciting question. We should be able to find out. I mean, at the very least, some history of mathematics book, but definitely. So Adiba, as Professor Barali was saying, to obtain a functioning, possibly feasible airfoil shape, you have to start with a disk that doesn't contain the origin. And definitely the picture I put out there doesn't do a lot of honor to the mathematical skills at NASA. At least, they should explain what those blue coordinate axes really meant.
I just want to make a comment here. See, what you talked about filling up gaps in that Droste images was using the map many times. But what Ingrid Dubeshi does is, restoring old artifacts where some things are missing.
Ooh.
So that could be a different technique.
Absolutely. That could be a different technique and a really interesting one to, I'm even thinking of, besides artifacts, even, I don't know, extinct animals, dinosaurs. You have only that little piece that you were able to recover. And how can you, right. But in the Droste thing, the feature that matters is that you are iterating the same image, right?
So it's very different, I think.
It's different, but somehow it's in a similar spirit, because what you're talking is about image reconstruction from a given fragment.
Okay,
And Droste is a very special case. It's a very special case where your image has this self-reproducing feature in it. But
you know
Yes.
exactly what to do there, right? While in the other one, I'm not so sure, like, you know, if it's a, say, painting of some.
Yeah, I think the general problem is much more difficult.
Yeah, because they have to
And,
match it, not just
exactly.
match it also, maybe it should look
Exactly.
like, go as close to original. I don't know how they do it, but yeah. So.
No, me neither. Maybe they, I'm just throwing it out there. Maybe they write models that are based on artifacts for which they have more information already.
Right,
And so
yeah.
based on that, you postulate that it could look like this and that, and then you model, you write
Yeah.
code for filling
So
it up.
she gave a beautiful talk in ICM 2018, and it should be available online still, I think.
What is this?
Ingrid Dubeshi gave
Oh,
a talk.
she gave a talk about this
art
kind of image.
restoration. Yeah,
Art
image
restoration.
Image restoration in 2018 Rio Art ICM.
I see.
It should
Fascinating.
be still online, yeah.
I will be looking it up. Thank you.
All right, I see another question. This is about, okay. So this is from Ankur Raj, who writes, ma'am, as you told while making the geographical map of the Earth, the center of the Earth was chosen for the purpose of projection. I suppose he's referring to the Mercator projection.
Mercator, right.
And the projection was made on a cylindrical sheet.
Yes. So on a sheet, so you have, in other words, if this is the Earth, pretend that this is a sphere. Okay. Actually, I can do better. I can use my lamp. Except that I can't. Let me see here. This is the Earth, right? We want to draw a map. And so we take this sheet and we wrap it around it, like, and obtain a cylindrical shape, paper shape, and then we apply the stereographic projection principle from the center of the Earth. And so what this does is give you a perfect reproduction in perfect scale of everything that's on the equator. And the further away you get from the equator, the larger the distortion. In fact, I forgot to mention, in that particular Rand-McNally Mercator projection, you will see that the Antarctica has been conveniently cut out. And the reason why it is conveniently cut out, because with that projection, projecting from the center of the Earth, Antarctica would go down to minus infinity, right? I mean, you would have. So, again, localization is key.
And in the process, you have answered his question, because having described this projection, his question was, but how are the north and south poles drawn?
Exactly.
As this would map to the infinity?
Exactly. And the answer is they're not. You just cut your piece of paper at a convenient place.
Right.
Well done. Well done. Thank you for pointing this up. Oh, and thank you for sharing this. Gita shared the link to Ingrid's talk. Very good. Excellent. Thank you.
So I don't see any more questions in the chat box, but there are people still in the meeting. Questions, people? Well, as people are pausing to ask, Loredana, I would like to ask, and this sort of talks to the theme of IWM, because we also want this an opportunity for people to sort of understand how active mathematicians do mathematics. How did they get to where they are? So I just wanted to ask you do you think that your experiences as a woman mathematician have 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 in some ways been distinct from those that the majority that still happens to be male share when talking about their journey into being a mathematician?
That's a really hard question, Gautam. I would be curious to hear what other speakers answered. It's a very important question. It's a question at the heart of the matter. So I cannot give a comprehensive answer because I cannot personally live through the experience of being a male mathematician and therefore compare, right? But I can tell you that I have been in my professional life, I've been in many situations where I was the only woman in the committee, in the room, at the conference, in the lecture, in the class, you know. And you know, it's never good when there is only just you that you can identify with in whatever context, you know, whether it's scientific context or professional, you know, educational, professional, personal. When you are the isolated singularity and there is no one that you can relate to, or at the same time, that may not be, what can I say, that hasn't had the same kind of experiences that you have had and therefore can relate to your own experience, always makes for difficult, you know, extra difficulties in life. And, you know, it creates a different level of awareness that you have to have at all time. It cuts off a little bit of playfulness and spontaneity. You know, this is just a silly example, but it might, you know, help somehow, you know, give an image, a little bit of an image to the question that you're asking. I remember when being a very young assistant professor, young, and by young I mean less experienced than I am now and less self-confident in my own capacity, or, you know, in my own ability to make mistakes, meaning when I was younger, I thought a mistake was the end of the world, and now I don't think about it anymore that way. So my approach to life has changed. But back then, when I was more fragile in so many different ways, I remember going to a conference where I was the only woman, and it just happened that I was the only woman, not just at the conference, but in the whole hotel where this was happening. So I remember there being a happy hour whereby, you know, people would be drinking drinks before going to dinner. And I remember clearly hearing people behind me telling one another, let's hear how much drink can she take. And I remember having to come up with strategies. It was a foreign country, so I didn't speak the language, but being Italian, I'm very good at mimicking. And so I made a little arrangement with the bartender whereby they would put 3/4 water in my drink. And so I was able to drink 3 drinks, which were really just one drink. But, you know, it gives you a little insight on the extent to which one needs to be constantly aware, self-aware, aware of what you say and how you say it. And it unavoidably, I think it's something that works for all of us at different levels, but in our profession and many other professions that are still, you know, demographically male dominated, it requires constant mindfulness. I don't know if that answers in any way.
No, it does. And in fact, you would have noticed I was quite tentative in asking the question because again, I do have to acknowledge such a vast segment of the math community today is still male, and I am very aware of comparatively the privileges I have, which is why, in a sense, it's only an intellectual knowledge that I have that your experiences in your road to becoming a mathematician were non-generic. And it's probably therefore also makes sense to break the question that I really had into two parts. And the second part was, what is a challenge that you've experienced professionally as a woman mathematician, and how did you overcome this challenge?
I think I'll start with the answer to the overcoming part. I think exercising mindfulness is the best strategy. The typical challenge that I faced and keep facing, but it doesn't affect me so much anymore because I'm better able at seeing it and detecting it, is this notion of subconscious bias. And, it takes a while to be able to detect a subconscious bias and also to detach yourself from being emotionally affected by it. The person who is practicing the subconscious bias most likely are not aware of it. And so it's not something on you, it's just something that's happening to them. So that you are not emotionally, you're not taken into this emotional, personal. It's not personal. It doesn't make it personal anymore. And there is a book that I want to recommend, which was recommended by I believe, our mutual friend, Malabika Pramanik. And I will put it in the chat box, if I may. I don't remember the title, but the authors, but the title is very distinctive. And the book is What Works for Women at Work. And it's written by a mother. There are two authors, and they happen to be mother and daughter. The mother is, I think, professor of psychology at some university in the United States, and the daughter at the time was a graduate student in sociology. And there is a particular chapter that deals with detecting subconscious bias. So many have happened to me, but I don't want to be too anecdotal because our world being such a small world, it would be very easy then, to solve the inverse problem, as you were saying. But it could be a typical subconscious bias that that I have run as a woman, and I hear it's rather frequent, is the fact that we are very often appreciated for our administrative skills and less so for our creative and originality inducing skills. If you look, they made studies of letters of recommendation. In the United States, letters of recommendation are very important in order to acquire positions in academia, for instance. And they did a blind study, and they realized of words, and then they sort of disclosed the gender of the person that was being written, the letter was being written about. And what's typical, scarily frequent, is that words like brilliant, original, inventive are associated with the male gender, and words like persistent, dedicated, reliable are associated with the female gender. And so it has sometimes happened to me that I've been called upon fulfilling tasks that would be best described by the feminine, so not feminine, female attributed features. And at that point, I would make the conscious decision whether taking on such tasks would have a negative impact on my own creative ability in terms of, I don't know, taking away the time that I had set up to do research, to work on this new project, so that I can fill those spreadsheets, and simply saying no, without bringing in, there you go, Erin, without bringing in, any subconscious bias thing or anything. You just say, you have something else that you're already busy with. But the point is, you have to be mindful. You have to be mindful, and you have to be ready. And at the same time, you have to accept the fact that most likely whoever this kind of requests are coming from are not really dictated by a personal perspective, but rather by a general position that they may not be aware of as well.
Thank you. I mean, I actually have so many questions that can be launched from your last couple of observations, but I should ask other people. Any questions in this connection?
Yeah, I would like to ask a question. Do you think it has changed now in recent time from, let's say, last 10, 15 years? Like, I also remember going to conferences where I was the only attendee, only speaker, woman speaker, and as a result, nobody knew that the bathroom door doesn't close at all, and I had to complain, and they said, no, everything is fine. So those kind of little things, like, they don't account for.
The little things that grind day in and day out constantly in our lives, right?
Yeah. So I mean, has it changed in recent time? So I also was in an institution, premier institution, where in fact our floor did not have a bathroom, and we had to keep running up and down to find a ladies' bathroom. Finally, I had to threaten that I'm going to use, there were two men's bathroom, one private and one men's. So I said, private doesn't mean men, so I'm going to start using that, whereupon they made, they converted part of it into a ladies.
Oh, that's marvelous, Gita, that you were able to find a solution.
But it took 3 years at
took
that
3
time.
years. Yes.
So
from the point of view of infrastructure, probably things are changing for the better, if nothing else, because they have to. Right now, there are, in many parts of the world, there are requirements. There has to be a women's bathroom, or even now all gender bathroom. Now we're beyond the two genders.
Yes.
And so there seems to me that if it's not being truly internalized, at least at the level of the official rules, there is more consideration for diverse needs. On a more personal level, I think, when it comes to subconscious bias, and I'm going to say something obvious, but sometimes you have to. My sense in interacting with many people is that subconscious bias, at least gender-based bias, seem to be less prevalent in junior mathematicians that I interact with now than mathematicians who are my age, or even more so my senior, So this gives me hope that as we slowly bring in more diversity in the academic field, then there's going to be more diverse role models that young people can look up to. And so you see, if you are a young male math student who has a female undergraduate advisor, or a female master thesis advisor, or a female PhD advisor, your view towards female mathematicians will be necessarily different than someone who has been taught only by male teachers. And so I can see that, the importance of role models is going to bring societal change. It is already, but we need to use a feminine gendered word, persistent. But I think I can see that when I interact with mathematicians, interacting with junior mathematicians is somehow easier, and a great part of it is because they have seen other women mathematicians that they have interacted with. So it's not such a strange experience, unusual experience anymore. Does that answer your question, Gita?
No, this is Riddhi.
Oh, sorry, Riddhi, sorry. Riddhi.
Partly, but so I have another related question. I mean, you're talking about young mathematicians and more women at maybe younger level, and also more male mathematicians, younger male mathematicians whose views are changing. But I also feel that somehow there are not enough women at the top, like in committees and all, who take decisions. So do you think that affects? I feel that because, it's the mindset. Even we get biased often. So.
Yes, it does. And in fact, what you just said, Riddhi, reminded me of a discussion I had a while ago with Jill Pfeiffer, who is a female American mathematician who has been the president of the American Mathematical Society, and prior to that, the president of the Association for Women in Mathematics. And the phenomenon you're describing, it's still very visible, I think, in the awarding of prizes. Prize for this and the prize for that. And it is very often the case in prize committees that are dominated by one gender, which is typically the male gender. You will see that the committee's job is to identify candidates. You solicit nominations, but you also actively look for candidates. And I have served in prize committees, and I have seen that this subconscious gender bias persists, because when you're asked to identify, a candidate for a prize, you think of someone that you look up to or that you can relate to, and without realizing that. And most often it happens that men will nominate men. And so, yes, we need to change this pyramid structure and put more women in the committee work, that the kind of work where decisions are made, as opposed to the kind of work where spreadsheets are being filled. And for that reason, let me put on the chat box something that might be of interest to you. There is a relatively new journal. It's called La Matematica, and it goes by Lama, or I think they use all uppercase, a new journal. Here. So, La Matematica is the new mathematics journal of the Association for Women in Mathematics. All the editors-in-chief are women, and there are 65 associate editors, which are very, I would say, well distributed in terms of gender and ethnicity. And so La Matematica is making a very conscious effort at being a high quality journal that is mindful of doing everything they can to subdue subconscious bias in the process of reviewing manuscripts and publishing papers. So, if I may, I would like to take this opportunity to encourage all of you to consider submitting your work, a future paper you're writing now, to La Matematica. And I know for a fact, I serve as an associate editor. I just do a little bit of the work that the main editors do. But I know that they're very, very conscious and mindful in the way that the decision process is being carried out. But so this is one instance, Riddhi, of what you were talking about. And definitely that needs to be changed.
Yeah, these days I feel more and more. We are doing this IWM activity, but then I also hear views from other people that, it's become a club, like, and why do we need to call women to a general conference? They are anyway giving talks in IWM. So,
Right,
so
right.
these kind of things keep happening. If you also have some advice to young, I would say not just girls, but young mathematicians, because you've gone through a successful professional mathematical career.
So this might be sounding like it's coming roundabout way, but I believe that it applies even to this context. This pandemic has been very hard on the entire world. I mean, there is no one who can claim that they haven't been affected by it. And during the past couple of years, what was very helpful to me was to somehow rediscover, because I had studied it in high school and then conveniently set aside. I rediscovered the Stoic philosophical thinking. Stoicism. Here. It's by Aaron. It's a way. It's a philosophy that goes back to the Romans and the Greeks, and the very Marcus Aurelius is one of the most well-known proponents from back in the Roman ages, and one of the guiding principles of the Stoic philosophy is that we humans, we have no control on what nature or other humans can bring upon us. The only control we really have is the way that we react to what life brings upon us. And so, once you accept this point of view, then you realize that there is very little that can truly hurt you or affect you unless you give it permission to. And practicing it mindfully and consciously can make you better equipped at accepting the difficulties that are part of our lives and they're part of our gender, and at the same time facing it. I was surprised to discover, just to mention NASA one more time, that learning about Stoicism is part of the training that NASA astronauts have to do when they go out for missions. And you know why? Because the Stoic mindset helps you to be the best of yourself and do the best that you can do, no matter what the circumstances that surround you. It doesn't mean that you're not going to be hurt or you're not going to be afraid by whatever happens to you if you're on a space station that's collapsing. But no matter what is happening, you will be capable of doing the best you can, which is all we can do, at the end of the day. And surprisingly, there is this not-for-profit movement that's been started, Modern Stoicism, in the UK, which is, it used to be just a couple of hundred people scattered here and there. And then with the pandemic and thanks to Zoom, it has skyrocketed, and they have these free events once or twice a year, Stoicans, where 4,000 people gather on Zoom, and there is this very well-designed, set of activities, which I found immensely helpful to navigate the pandemic. And now that we're starting to perhaps see, from a distance, the beginning of the end of it, I'm realizing that actually it's helping me in my everyday life, in my work, in the way that I relate with my colleagues, with my family. And so this would be my recommendation. Try and see if you can do a little bit of reading up on Stoicism and see to what extent it can help you face in a more serene and effective way the unavoidable challenges that life presents us with, and in particular the challenges that come from being professionals in the profession that we have chosen.
More questions? So we are fairly close to the end of our 2 hours, and which I think, so Loredana, it would be 1:30 p.m. in your part of the world. Am I right?
It is. It's 1:32.
1:32. Yeah.
Another typo. I can't believe it. There's another typo. Okay, I will not try a third time. But the first word is correct in the first, and the second one in the second.
So since we are almost at the end of our 2 hours, I just want to sort of close out by making an observation I saw on the chat box. This is by Professor Ajit Iqbal Singh. And I didn't know she has an eye for the one thing that entertains me a lot, which is alliterations. So you named this book, What Works for Women at Work? And it's almost an alliteration. www. And so Professor Singh just wanted to share with us that Coulson would, at the end of the proof, instead of writing QED, would write W to the power 5, which means which was what was wanted.
That's terrific. I will do that. Thank you.
Yeah, I'm extremely tempted. In fact, I lecture on Friday, and instead of drawing a small box, I just want to write W to the 5 going forward. I want
Fantastic.
to see. So this, people, brings us to the end of our 2 hours. So, okay, there's
Gautam, I changed it to W raised to 6. Wonderful, which was what was wanted.
Ah, thank you
Yes.
so much. Wonderful.
Even better, even better.
Fantastic.
Marvelous.
I did not notice that.
Absolutely.
So Professor Ajit Iqbal Singh is our senior mathematician, woman mathematician, and inspiring to everybody around. And she attends all the talks of many different subjects and makes connection and knows, very wise mathematician, very senior too.
Congratulations. We need more people like you.
Wise women around, Riddhi Shah and all.
Ajit, please.
She is right. All right, so we are a little past the 2 hours for this session today, and I am glad that we ended hearing the word wonderful. This was truly wonderful. So I would like to thank Professor Lanzani for a wonderful talk. And I congratulate you, Loredana, for taking the decision that you took, because you specifically wrote to me saying that, no, this is the talk I want to give. This is not about my research, but there is a lot that is thought-provoking. You are absolutely right. It's by looking at a couple of words in your abstract that I spent an entire evening looking up on Google the work on morphometric analysis and the various directions that it's kind of taken off on. So indeed, first about your talk, I think I speak for everyone when I say that we've learned a lot of things in the way that you structured your talk.
Oh.
And also speaking for myself, but I think I speak for everyone present, that we learned a lot of things from the specific viewpoint that you were coming from about your life and development and how one becomes a mathematician. This was a very, very refreshing viewpoint, and we indeed learned a lot. I am very, very grateful that you accepted our invitation. So I hope everyone will share me for another round of applause.
Oh, thank you. And on my end, I have to say that this has been the most engaging and the most, and I mean it in a happy way, mind challenging conversation I've had in a very long time. Thank you. Thank you. It's a joy to talk with you and hear about your work. Thank you.
Thanks so much. And thank you, everybody, for attending. Take good care. And I really hope that more people have Gita's experience, which is that we get to start teaching in person. Fingers crossed.
Absolutely. Absolutely. Stay, and in the meantime, stay safe.
Yes, you too. Thank you so much.
Thank you.
And bye now.
Bye.
And with those words, I bring an end to this meeting.
So I'm ending this meeting, right? So is it okay?
Yes.
Okay. Bye, Riddhi. Bye, Gita. Bye, Gautam.